Hello, all of you again. I'm here for my weekly analytics challenge. Last week, I'd asked a question about what's the minimum number of people in a room where you can expect to have a 50% probability of at least two people having the same birthday. Some of you got the answers right, but you can always Google and get the answer. The answer is 23. So if there are 23 people in a room, the chances are that there'll be at least two people who have the same birthday, and that chance is 50%. Okay, how do we get to that number? So, I wanted to share with you how do you solve such kind of probability questions. And there's a very simple way to go about doing it. Let us assume for a moment that there are only two people in a room. If there are only two people in a room, the chance or the probability that they would have the exact same birthday would be if both of them share one day out of 365 days. So that probability would boil down to 1 out of 365, which means if you need to reverse the problem, the probability of them not sharing the same birthday would be 364 days out of 365 days, which is the probability of 99.7% that they would not share the same birthday. Well, that seems pretty dramatic. That seems, pretty bad. Uh, what? So the probability that they would have the same birthday, therefore, boils down to only 0.03%. If there are two people in a room, the probability that they would have the same birthday is 0.03. But now let us take it to the next level. Let's say there are three people in a room. Now there are three possible combinations. You could have the first person having the same birthday as the second person, or you could have the second person having the same birthday as the third person, or you could have the third person having the same birthday as the first person. So instead of now only two people, you are now comparing between three possible equations. Therefore, the equation changes. Now the probability of not having the same birthday becomes 364 divided by 365 to the power of 3. Why 3? Because there are three possible combinations. So that gives us a probability of 99.2%. You see, just by adding one more person into the room, we have reduced the probability of not having the same birthday significantly, which means the probability that two people have the same birthday among three people in a room becomes 0.008, which is 0.8%. Not good enough. I mean, it's not going to get us to what we want to get to. But you see where we are going? Every increase of a person in a room increases the probability that two people have the same birthday. Let's now look at four people in a room. The moment you have got four people in a room, there are possible 6 combinations of any two people having the same birthday. And therefore, what does it do? So your probability of not having the same birthday goes up to 364 divided by 365 to the power of 6, because now there are 6 possible combinations. And that brings that down to 0.984, which means the probability of two people sharing the same birthday in a room of four people is 0.016, which is not bad. Now we are improving. Now let's take that to five people. The moment you've got five people in a room, that five people takes it to combination of 10, and the combination of 10 improves the probability of two people in a room sharing the same birthday 0.027, which is 2.7%. We increase that from 5 to 6 people in a room. And the moment you have 6 people in a room, the combinations now increase from 10 to 15 possible combinations. And with 15 possible combinations, the probability of two people in the room having the same birthday improves to 0.04, which is 4%. Now let's play the game faster. And now I'm going to take it from 6 to 12 people in a room. Now you know how it works. The way it works is every time you keep adding one more person in the room, the number of combinations increases exponentially. It is not a linear increase in combinations. So by the time you have got 12 people in a room, you have actually got 66 possible combinations of any two people who could share the same birthday. With 66 people in the room, your probability that two people don't share the same birthday now goes up to 364 divided by 365 to the power of 66, which is bringing the probability of two people having the same birthday up to 16.6%. Right? So if you see, every time I'm increasing one person, my probability improves not by 1%, it improves by a lot. By the time I get to my 12th person, therefore, I have got a probability of 16%. By the time I get to my 13th person, I get to a probability of 19%. By the time I get to the 14th person, I get to a probability of 22%. And as I keep increasing the number of people in the room, by the time I reach my 23rd person in the room, I have a probability of 50.04, which means by that time, I would have gone up to getting a 50% probability that I would have at least two people in the room sharing the same birthday. If I now, what happens if if I'm really now looking for getting to 100% probability, when do you get 100% probability? The only way you can get 100% probability is when you have at least 366 people in the room. That is when you get a 100% probability. And that's the beauty of the tail of a probability curve. The tail is extremely long. So to get a 50% probability, you only need 23 people. But to get to 100% probability, you need 366 people. I hope you enjoyed this. So here is the analytics challenge for this week. All of you have heard about Charles Darwin. He is considered to be have written some of the most seminal work on the origin of species and how human evolution happened. Now you might all be thinking, what's the connection between Charles Darwin and analytics? One of the earliest concepts which was developed with regard to analytics is the concept of correlation. Today, correlation is a much abused term. It is used by anybody and everybody to explain anything and everything without much of a statistical thought. But when it was first applied, it was applied with a lot of thought. Today, most data scientists continue to use correlation with caution. Okay. And here is the challenge for this week. What is the link between Charles Darwin and the evolution of the concept of correlation? That's the challenge for you for this week. Not an easy one. Again, it's a tenuous link, but this is something that you would love to look at. So do get back to me with your answers, and here's to many more analytics challenges.